When dealing with junction boxes containing multiple home runs from different panels, a specific rule applies to the equipment grounding conductors. The requirement is that two separate equipment grounding conductors must be run. This means that you cannot simply splice the equipment grounding conductors together in the first box and then run a single grounding conductor in the conduit. The National Electrical Code, or NEC, mandates this separation for several important reasons related to electrical safety and fault current management. Firstly, maintaining separate equipment grounding conductors ensures a low impedance path back to each respective source panel. This is critical for effectively clearing ground faults. In the event of a fault, a large amount of current will attempt to return to its source. If the grounding path has too much impedance, meaning resistance to alternating current, it can impede the flow of fault current. This impedance can prevent other current protection devices, such as circuit breakers or fuses, from tripping quickly enough to prevent dangerous conditions. These dangerous conditions can include electrical shock hazards, overheating of conductors, and potentially electrical fires. Secondly, the separation of equipment grounding conductors helps to minimize the risk of circulating currents. When multiple sources are involved, combining the grounding conductors can create a loop. This loop can allow unwanted current to circulate, especially if there are slight voltage differences between the grounding systems of the different panels. These circulating currents can cause unnecessary heating of the conductors, energy waste, and interference with sensitive electronic equipment. Thirdly, the NEC requires that the size of the equipment grounding conductor be based on the size of the ungrounded conductors in the circuit. When you combine multiple circuits into a single conduit, it can become challenging to properly size the single equipment grounding conductor to adequately protect all the circuits. By keeping the grounding conductor separate, you ensure that each circuit has its appropriately sized grounding conductor, providing the necessary level of protection. To properly install the equipment grounding conductors in this scenario, run each equipment grounding conductor from each panel's home run independently into the junction box. Then continue each grounding conductor separately through the conduit to the equipment being served. Do not splice or combine the grounding conductors within the junction box or anywhere else in the run. Each grounding conductor must maintain its independent path back to its respective source panel. It is also important to ensure that all connections are made properly and are mechanically sound. Use appropriate connectors and ensure that they are properly tightened to provide a low impedance connection. Using the correct size of equipment grounding conductor is crucial for safety. The size of the equipment grounding conductor is determined by the size of the overcurrent protection device, such as a circuit breaker or fuse, protecting the circuit. Refer to NEC Table 250.122 for the minimum size requirements for equipment grounding conductors based on the size of the overcurrent protection device. For example, if the circuit is protected by a 20 amp circuit breaker, the minimum size for the copper equipment grounding conductor is typically 12 American wire gauge or if the circuit is protected by a 30 amp circuit breaker, the minimum size is typically 10 AWG. Always consult the NEC table for the specific requirements based on the size of the overcurrent protection device and the type of conductor material being used. In addition to the size requirements, it's also important to consider the type of equipment grounding conductor being used. The NEC allows for various types of equipment grounding conductors, including copper conductors, aluminum conductors, and rigid metal conduit, or RMC. Copper conductors are the most common type of equipment grounding conductor used in residential and commercial applications. Aluminum conductors are also permitted, but they must be sized larger than copper conductors to provide equivalent conductivity. RMC can also be used as an equipment grounding conductor, provided that it meets certain requirements outlined in the NEC. These requirements include ensuring that the conduit is properly installed with listed fittings and that it provides a continuous electrical path back to the source. When making connections to equipment grounding conductors, it is important to use listed connectors that are specifically designed for grounding purposes. These connectors are designed to provide a low impedance connection and to withstand stresses of a fault current. Do not use wire connectors that are not specifically listed for grounding purposes, as they may not provide an adequate connection. Proper grounding is a critical aspect of electrical safety, and it's essential to follow all applicable codes and standards. If you are unsure about any aspect of equipment grounding, consult with a qualified electrician or electrical engineer. Improper grounding can create dangerous conditions, including electrical shock hazards and fire hazards. When running the equipment grounding conductors, ensure they are installed in the same raceway, cable, or cord as the circuit conductors. This ensures that the impedance of the grounding path is minimized. The NEC requires that the equipment grounding conductor be installed in close proximity to the circuit conductors to reduce inductive reactance, which can impede the flow of fault current. Additionally, avoid making any unnecessary splices in the equipment grounding conductor. Splices can introduce additional resistance into the grounding path, which can reduce its effectiveness. If splices are necessary, use listed connectors and ensure that they are properly made and tightened. When working with electrical systems, always follow safe work practices. To energize the circuit before working on it, and use appropriate personal protective equipment, or PPE, such as gloves and safety glasses. Verify that the circuit is energized using a voltage tester before touching any conductors. If you are not comfortable working with electrical systems, hire a qualified electrician to do the work. Remember that electricity can be dangerous, and it's important to take all necessary precautions to protect yourself and others. The principle of keeping equipment grounding conductors separate when dealing with multiple home runs from different panels is not merely a suggestion, it is a code-mandated requirement rooted in safety and the reliable operation of electrical systems. It's about ensuring that each circuit has a dedicated and effective path for fault current to safely return to its source, tripping the necessary overcurrent protection devices quickly and efficiently. By adhering to this practice, you minimize the potential for electrical shock, equipment damage, and fire hazards. In practical terms, this means meticulously running each equipment grounding conductor from its originating panel, maintaining its individual integrity throughout the junction box and onward to the equipment it serves. No shortcuts, no splices, no compromises. Each conductor acts as an independent lifeline, ready to spring into action the moment the fault occurs. Ignoring this requirement can have serious consequences. If the equipment grounding conductors are improperly combined, the fault current path may become compromised, increasing impedance and slowing down the response time of overcurrent protection devices. This delay can allow dangerous voltages to persist on equipment enclosures, posing a significant shock hazard to anyone who comes into contact with them. Furthermore, the undersized or compromised grounding path may not be able to handle the full magnitude of the fault current, potentially leading to overheating of conductors and insulation, increasing the risk of fire. Beyond the immediate safety concerns, improper grounding can also negatively impact the performance of sensitive electronic equipment. Circulating currents caused by combined grounding conductors can introduce noise and interference into the electrical system, disrupting the operation of computers, communication devices, and other electronic equipment. In conclusion, the requirement to maintain separate equipment grounding conductors in junction boxes with multiple home runs from different panels is a non-negotiable safety measure. It ensures a low impedance fault current path, minimizes the risk of circulating currents, and protects both people and equipment from electrical hazards. By understanding and adhering to this principle, you contribute to a safer and more reliable electrical system. Consider a scenario involving a metal enclosure that houses sensitive electronic equipment. This enclosure is fed by two separate circuits originating from different electrical panels. Each circuit is protected by a 20-amp circuit breaker and includes a 12 AWG copper equipment grounding conductor. According to NEC Table 250.122, a 12 AWG copper conductor is sufficient for a 20-amp overcurrent protection device. However, if the two 12 AWG equipment grounding conductors were spliced together in the junction box and a single 12 AWG conductor was run to the metal enclosure, the grounding path would be inadequate. Although the 12 AWG conductor may be sufficient for a single circuit, it would be undersized for the combined fault current potential of both circuits. In the event of a ground fault within the metal enclosure, the undersized equipment grounding conductor may not be able to handle the full fault current, potentially causing it to overheat and increasing the risk of fire. Furthermore, the increased impedance of the undersized grounding path could slow down the response time of the circuit breakers, allowing dangerous voltages to persist on the enclosure and creating a shock hazard. By running two separate 12 AWG equipment grounding conductors, one from each circuit, the metal enclosure is provided with a dedicated and adequately sized grounding path for each circuit. This ensures that the fault current is safely and quickly conducted back to the source panel, tripping the appropriate circuit breaker and minimizing the risk of electrical shock and fire. Now consider a situation where an electrician decides to use a single, larger equipment grounding conductor to serve both circuits in the aforementioned setup. The electrician reasons that by using a larger conductor, they can provide an equivalent or even better grounding path compared to using two separate conductors. For instance, they might choose an 8 AWG copper conductor to replace the two 12 AWG conductors. While this approach might seem logical on the surface, it still violates the NEC requirement for separate equipment grounding conductors. Even though the 8 AWG conductor has a lower impedance than a single 12 AWG conductor, it does not provide the same level of protection as two separate 12 AWG conductors. The primary reason is that the fault current from each circuit must still travel through the same single conductor. In the event of a fault in one circuit, the entire fault current would be concentrated in the 8 AWG conductor, potentially overloading it and increasing its temperature. This could lead to premature failure of the conductor and an increased risk of fire. Furthermore, the electrician's approach might create confusion for future electricians or technicians who may not realize that the single conductor is serving multiple circuits. This could lead to improper troubleshooting or repairs, potentially compromising the safety of the electrical system. The NEC requirement for separate equipment grounding conductors is not just about conductor size, it's about ensuring that each circuit has its own dedicated grounding path. This provides the most reliable and effective protection against electrical faults. To further emphasize the importance of separate equipment grounding conductors, let's consider the scenario of a branch circuit supplying power to a sensitive piece of electronic equipment in a commercial building. This equipment is critical for the building's operations, and any interruption in power could result in significant financial losses. To ensure the reliability of the power supply, the electrician decides to run two separate branch circuits from different electrical panels to the equipment. This way, if one circuit fails, the other circuit can continue to provide power, minimizing downtime. However, the electrician makes a critical mistake by splicing the equipment grounding conductors from the two circuits together in a junction box and running a single equipment grounding conductor to the equipment. This creates a common grounding point for both circuits, which can introduce several problems. Firstly, any noise or interference present on one circuit's grounding conductor can be coupled onto the other circuit's grounding conductor, potentially disrupting the operation of the sensitive electronic equipment. This is because the equipment grounding conductors act as antennas, picking up electromagnetic interference from various sources. By combining the grounding conductors, the interference can be amplified and transmitted to both circuits. Secondly, if there is a ground fault in one circuit, the fault current can flow through the common grounding conductor and potentially affect the other circuit. This can cause voltage fluctuations and transients on the second circuit, which can damage or disrupt the operation of the electronic equipment. In addition, the common grounding conductor may not be able to handle the combined fault current from both circuits, potentially leading to overheating and fire. By keeping the equipment grounding conductors separate, the electrician can isolate each circuit and prevent noise, interference, and fault currents from affecting the other circuit. This ensures a more reliable and stable power supply for the sensitive electronic equipment. It is also important to consider the potential for ground loops when multiple circuits share a common grounding point. Ground loops occur when there are multiple paths for current to flow between two grounded points, creating a loop. These loops can induce unwanted currents in the equipment grounding conductors, which can cause noise, interference, and even equipment damage. By keeping the equipment grounding conductors separate, the electrician can avoid creating ground loops and ensure a cleaner and more stable electrical system. Another scenario involves a residential application where an electrician is installing a new subpanel in a garage. The subpanel is fed by a feeder circuit from the main service panel in the house. The electrician runs the feeder conductors, including two hots, a neutral, and an equipment grounding conductor, from the main panel to the subpanel. At the subpanel, the electrician bonds the neutral and equipment grounding conductors together at the neutral bus bar. This is a common practice in subpanels, but it can create problems if there are multiple branch circuits originating from the subpanel and feeding different loads in the garage. If the electrician splices the equipment grounding conductors from these branch circuits together in a junction box before running them to their respective loads, they are creating a common grounding point that can lead to the same issues as described earlier. Noise, interference, and fault currents can be coupled between the circuits, potentially affecting the performance of sensitive electronic equipment or creating a shock hazard. In addition, if there is a ground fault in one circuit, the fault current can flow through the common grounding conductor and potentially affect other circuits. To avoid these problems, the electrician should keep the equipment grounding conductors from the branch circuit separate and run them directly to their respective loads. They should also ensure that the neutral and equipment grounding conductors are only bonded together at the main service panel, not at the subpanel. This will help to prevent ground loops and ensure a cleaner and more stable electrical system. It is also important to consider the impact of harmonics on equipment grounding conductors. Harmonics are distortions in the alternating current waveform that can be caused by nonlinear loads such as electronic devices and fluorescent lighting. These harmonics can create additional current flow in the equipment grounding conductors, which can lead to overheating and equipment damage. By keeping the equipment grounding conductors separate and properly sized, the electrician can minimize the impact of harmonics on the electrical system. In some cases, it may be necessary to use a dedicated equipment grounding conductor for each circuit to further reduce the effects of harmonics. The NEC also requires that the equipment grounding conductor be installed in the same raceway cable or cord as the circuit conductors. This helps to minimize the impedance of the grounding path and ensure that the fault current can flow quickly and easily back to the source. It is also important to avoid making any sharp bends or kinks in the equipment grounding conductor, as this can increase its impedance. The equipment grounding conductor should be installed in a smooth and direct path, with minimal bends and obstructions. In addition, the electrician should ensure that all connections to the equipment grounding conductor are properly made and tightened. Loose or corroded connections can increase the impedance of the grounding path and reduce its effectiveness. Listed connectors should be used for all grounding connections, and they should be torqued to the manufacturer's specifications. It is also important to protect the equipment grounding conductor from physical damage. The conductor should be installed in a location where it is not likely to be damaged by impact, abrasion, or corrosion. If the conductor is exposed to physical damage, it should be protected by conduit or other suitable means. In addition to the NEC requirements, there may be local codes or regulations that apply to equipment grounding. The electrician should consult with the local authorities to ensure that they are following all applicable codes and regulations. Proper equipment grounding is essential for electrical safety. It protects people from electrical shock and helps to prevent equipment damage and fires. By following the NEC requirements and best practices for equipment grounding, the electrician can ensure that the electrical system is safe and reliable. Remember that electricity can be dangerous, and it is important to take all necessary precautions when working with electrical systems. If you are not comfortable working with electrical systems, hire a qualified electrician to do the work. The scenarios described provide practical examples of why it is necessary to maintain separation.